differential equation, it decreases to 0 without crossing it and without oscillations. And just if we take now tau greater than this threshold, the solution will oscillate all the time around 0 and go to 0. And the solution will go to 0, but with the oscillations, damping oscillations. And there is another threshold. If we are bigger than this threshold, we have periodic solutions. Just when tau is greater than this point. What is important here is all the solutions oscillate. You can change your initial condition as you like to have all the time oscillations, except the trivial solution. But all the solutions oscillate. And this is the numerical simulation of this model. If tau is, for example, here less than the threshold, you have the solution decrease go to 0. Here also there is like a small oscillations as such. Here we can see really oscillations, and after that it becomes periodic. Okay, and we can explain it by this. The only part difficult is to have periodic oscillations using these polynomial functions. By hand, it's very difficult, but we can prove it analytically. And of course, it doesn't depend on the initial condition. This is, we take here 1, it's more easy, but you can take continuous initial condition, different from this general one, you will have the same behavior. And this is why this is the question, because in our system, in our ordinary differential equation, there is only one parameter. And one is here, this point, and also this point. And I will show you after all the delay differential equation, we will find these 2 points. This one, it's only approximation. I will give you the real value of this point and the real value of this one. I will do it here. It's 1 over exponential is. Sorry? Always, yes. Always appears, it depends on if you have system, but always, and also this one. Always. And what is more interesting for this one, I told you 1 tau is greater than 5 over 2, because I took this approximation, but the real value is this one. If we take tau greater than this, periodic solutions appear, but we know the period is period 4, exactly 4. This is interesting. In fact, we can show, we will show it analytically, that all solutions oscillate when the delay for this center is greater than 1 over exponential. And what that means, oscillations, it means cross 0 forever. This is exactly what you are expecting. Yes. And 1 tau is greater than, yes, this also between 0 and 5 over 2, we always go to 0. But when we are greater than this threshold, we will not go to 0, but the solution will go around the limit cycle. Periodic solutions. And what I showed you before for this system. I will come back to, yes, this one. These two solutions will be like the main base of this limit cycle. Always cosine and sine. In fact, I was talking about this delay differential equation that is the simplest one. In fact, all the delay differential equation like this can be we can reduce it to this by changing the solutions and making change of coefficients. At the end, this and the other one, they are equivalent. Okay, because if we take this this one more general, and if we take this change of function, we take x of t equals exponential minus kt y of t, and you put alpha minus v exponential minus a tau, then you get this. It's very easy to, if you calculate the derivative of this and using this change of parameters, you obtain exactly this one. Okay, that means this is equivalent to this. And you can do it in the other side. You take y of t equals exponential equals x. You start from here and you obtain this. Okay, this is what we. Now we can, of course, we know the parameter alpha here using the other parameters stated in. And tau, the delay is the same. If tau equals to 0, this is only, now I will put this definition, but I will give the exact definition after. Asymptotically stable means that all the solutions will go to 0. Okay. If tau equals to 0, we know that if you take tau equals to 0, you will have ordinary differential equation, and we know that 0 is asymptotically stable if alpha is positive. That means the coefficient here is negative. And for tau equals to 0, it's unstable if alpha is positive. That means we have an exponential that go to plus infinity. And now if we suppose that tau is bigger than is positive, we will make change of time. I put instead of t, I put s equals eta t with eta positive, and we put capital X of s equal small x of t, and if we take the derivative at the end to obtain this. That means if we take this equals 1 over tau, we can put here tau equals to 1. What I want to say is we can make change of the differential equation to put here tau equals 1, or to put here 1, because we can also put eta equals to alpha, and here we will have, because eta is free now, we can put here 1 or put here 1. That means we can choose theta equal alpha and r equal. We can obtain this, it's equivalent, or this one. All of them are equivalent. That means we have like 1, 2, 3, 4 equations that are equivalent by change of parameters. This is why you will see sometimes I will study this, sometimes this one, sometimes the other one. At the end, it's have the same. We obtain the same result by making this change. Maybe we stop. Have a rest. Thank you.